There's a couple other things I want to discuss as we move on to try and get to talk about molecules. The next one we're not going to do, I think, a full justification for, but we're going to talk about it. So the variational principle. So far, we've talked about how we need to make approximations in order to solve anything with a greater than 1 electrons, right? We came up with these Slater determinants, try and show what's happening, but when we evaluate their energy, how does that compare to the real energy of the system? That's what the variational principle is about. It's kind of like it's a mathematical proof you can go through to justify that whatever energy you calculate with your new approximate stuff will either be at the energy of the true system or higher. So you're not going to get lower energy and lead you to something false in that regards. So if an arbitrary or approximate wave function is used to calculate the energy, the value calculated is never less than the true energy. Jeez. So we use an arbitrary wave function, or we say it that way. What we really mean there is our approximate wave function. So we're never going to calculate less than the true energy. Let's go through a justification to show that that is indeed true. Because we use this idea in a lot of other areas, and you have used this actually in a lab with your different approximations. Every energy you get out there or have gotten has either been higher or equal to the true energy of the system. Okay, we're going to consider a normalized and orthogonal trial wave function. This trial wave function is comprised of a basis set. What a basis set is it's the mathematical formulation to make the wave function. This is our basis set. It's kind of related to our orbital approximation that we've dealt with in the past. And this tells you the contribution of that function to the overall. Okay? We'll apply that to molecules in a bit, and it makes a little more sense when we get to molecules. Until we get there, the associated energy is given by So we can use that to get our energy out. That's our trial wave function, the true wave function, which we're going to give the symbol psi naught. Gives the true energy. Which we're going to call E naught. And what we want to calculate is the difference between these two energies. So we know how good our approximations are. So consider the difference between E and E naught. So E minus E naught is going to be equal to we could apply this guy, this integral in here, which we're going to do. But then we also could evaluate that integral for our true wave function. What we'll get out is this. Okay. We can rearrange some stuff around. Since this is a scalar quantity, we can just move that in. So all we've done is applied this. We've subbed in for here and just multiplied by this thing. What you eventually end up with is the following. So you can do some manipulation to get there. It doesn't take very much. All right. However, our trial wave function is made up of a bunch of basis sets because that's how we can represent these wave functions. So we're going to sub those basis sets in. Subbing. We're going to get this as an expression. Star, oops. E naught. Okay. What I want to do next is I want to aggregate these C's. Those C's are constants, so what could we do to this? Yep. We're going to pull those constants out. And we have some expressions for these guys. We're going to look at this integral in here. If we have the integral of this, what we can say is that's equal to the energy of our system. So we're going to get E to the N we can pull it out that way. And then we have to worry about this other bit in here. dt. What can we do with that E naught since it's a constant? Okay, we're almost there. So now let's take that and plug that into what I just erased. Oops. Then what we get minus E naught dt. We can say that it's true to E sub n minus E naught integral of that guy. There we go. Okay, and this whole thing we have shown is also equal to E minus E naught. Okay, so now these guys, they're orthogonal. What does that mean? They're 0 or 1. I guess I should have put a prime here. If n is equal to n, what's the value of it? Nope. That one's 1, right? If they're the same function, if they're different functions, then that integral is 0. So what is it going to be in this case? If n is equal to that other index, then we get that guy. Oops, I forgot some stuff. I forgot crap in here, I'm sorry. What I forgot to include was that guy. So I need to include that summation. Okay, and since Cn star Cn has to be greater than or equal to 0, and En minus E naught has to be greater than or equal to 0. Then we end up with the following expression. Summation n Cn star Cn. That all has to be greater than or equal to 0. Okay, a lot of math, a lot of crazy stuff going on here. Sorry, we ran through a lot of different things. What we're going to do now is we're going to transform this into relating that guy to this guy. So this was of our trial function, right? We wanted to look at that energy difference, and this should be the energy of whatever we input, right? If you manipulate this around, what you'll end up getting is that the energy for whatever system we calculate based upon our approximate or trial wave functions has to be greater than or equal to our actual ground state energy. Okay. Excuse me. Now, we're going to use this idea in our very last class on Monday and explain what's going on there. And then we're going to apply what we've learned today and on Monday to a small system through Huckel theory. Okay? There was a lot of information flying at you at once over the weekend. If you can, try to just investigate what the variational principle is. The big point, the big take-home message is this. We mathematically prove whatever we calculate, whatever its energy is of our approximate wave function, has to be greater than or equal to the true system. What is the best case scenario? They're equal. Okay? But we're not going to predict something that's lower in energy than the true system. Okay? All right, any questions about that? Okay, next time we're going to start talking about molecules, what a chemical bond is, fly through a bunch of information, and then try to get to Huckel theory. Okay? All right. Arts and Science Expo today, you'll be there.